Hi everyone, good afternoon. This is Mohammed speaking. I'm actually giving an overview of the flow in conduits, the chapter 10. But before that, we'll actually go through the lectures like the momentum equation and the energy equation. But in the final exam, these two chapters you just need to go through, but you don't need to solve any problems with it from the chapter 6, the momentum equation, or the chapter 7, the energy equation. There will be no problem, but there could be some the laws and the definitions. Those are important in here. So the chapter 6, at first we have learned about the Newton's second law of the motion, and from there we actually learned like different examples of different forces, like the body force and the surface force for the fluid and solid. Like we're more interested in the fluid, that means like the pressure force, shear force, buoyancy, drag force. So all of these different types of force. Later on we have learned about the second law of Newton's second law, and that is the summation of all external forces combined is equal to mass times acceleration. Okay, and from there we have developed the linear momentum equation, and we all are very much aware about how the momentum equation can be derived, because we already have derived the continuity equation, where in continuity equation we actually assumed like B extensive properties, B is equal to mass, and thus all the intensive properties, or like the smaller intensive properties, turned 1. But in here, in this case, we actually replace it with velocity. Okay, and then that's how we actually derived the momentum equation. And the next chapter, the energy equation, we'll actually derive in the same manner. So if you know how to derive the continuity equation, then it's like the very similar pattern we actually derived like the momentum equation, and so on. So here is our final form of momentum equation. So what is that? That is the net force equal to momentum accumulation plus the net momentum flow. So similarly, just exactly same with the continuity equation. Okay, so the continuity equation had like input minus output plus accumulation is the net flow. Okay, so that was for the net flow. Here we are learning the net force. Okay, so it's the very similar type. Now these are like the interpretation, like the physical interpretation. That means like the momentum of all particles are the summation. That really explained. And all the things like here we just as I said, we don't need to solve any problems. We just need to know what is the momentum equation, okay, and how it actually works. So this is the general equation. This is the simplified version, just like the similar with the continuity equation, where in continuity equation it was summation of minus mass output of the mass minus inlet plus accumulation is equal to total mass flow rate. Here, like the summation of all forces would be the sum of the net force working plus in outlet minus inlet. Okay, the similar pattern. And we all know like there is a reference frame. If you actually remind, when we actually solve the ANSYS problem, there is a reference value, there is an option, the reference value. Okay, so that is actually the reference frame. And in case of pipeline, we assumed the reference frames at like the inlet, right? Remember, at the inlet. Okay, here in case of if it's a rocket, okay, so it would be at the ground. It's the reference frame in here. So is the angular momentum equation. We'll actually skip the angular momentum equation. This is just a form. Okay, it's like the very similar way we derived. Now this is about the momentum equation, and the second part was the energy equation. Let's go to the energy equation. Here it is. So in chapter 7, again, you don't need to solve any problems in here. You just need to we'll just go through. You just need to know what is energy equation. That's the only thing I care, because at the chapter 10, the concept of energy equation, momentum equation would work. Okay, so we know energy. What is energy, and what is the definition of energy, and the classification of energy. This is important. Like what are the classifications? Like mechanical energy, thermal energy, chemical energy, electrical and nuclear energy. Okay, so these are like the different types of energy we have. And here, what are the units of the energy? It's mainly we calculate with joule, but joule is the SI unit, but sometimes we also use the British unit, which is called like the BTU, or other units like the calorie. Okay, so calorie is from um, the conversion is 1 calorie equal to 4.2 or 4.187 joule actually. Okay, so this is the conversion rate. And so energy, and there it goes the work. What is work? This is the definition. I'm pretty much sure you know about it already. So this is the definition of work is force times distance. Okay, and power is a quantity of work over the time. So work or energy over the time. Okay, so that would be mainly like the rate of change of energy or rate of work is power. Okay, so we usually explain it as a horsepower. Okay, so why horsepower? Because it is assumed like one horse can drag that amount of work. Okay, so that's how this horsepower unit actually developed. So the conversion is 1 horsepower is equal to 746 watts. Okay, so these are pumps and turbines. So mainly turbine is a machine that used to extract energy from the fluid, and pump works in the other way around. Okay, so what pump do is you have to provide energy and then it flow the fluid. So pump and turbine, they work in a different way. Like, I mean, if you just change the mode. Okay, so for instance, with a turbine you produce energy using the fluid's motion. Okay, but in case of pump, you are using energy to create the fluid's motion. Okay, so these are the differences. And we all are aware about like the theory of energy conservation, work, heat transfer. Okay, so this is the typical energy balance. Like we know there's a kinetic energy and potential energy and internal energy. Okay, internal energy works at the molecular level. So like the total energy would be kinetic energy plus potential energy plus internal energy. Okay, so that's how we actually derive our energy equation from the first law. Okay, and here comes the control volumes approach, and then we actually got the final terminology of the energy equation. And here you can see this is the final terminology of the energy equation. What is important in here is these portions. I'm actually showing you here. This is the final form, and here these portions. Okay, so here is the terms as mechanical energy. These are like the thermal energies. Now just think about like the mechanical energy. Okay, so here one term is the head loss. Now this is an important concept. Okay, what is the head loss? And this head loss will actually later on at the chapter 10, the whole chapter is actually based on like how we can calculate this head loss. Okay, so this head loss is when you actually get the final form of the energy equation is the Bernoulli's equation plus this head loss. Now HP is for the pump, T for the turbine, but this HL, this is the head loss, and this head loss occurs mainly due to the friction. Okay, so that's we will actually learn from chapter 10. And these are like, for alpha they're like laminar or turbulent, so these are like the just some factors. Okay, so these are like the engineering factors we have for that. So these are the interpretations. Okay, so this is important portion. So this portion is like the pressure head, velocity head, and elevation head plus pump head equals to, at the point 2, pressure head, velocity head, and elevation head plus turbine head plus head loss. Okay, so this is how we'll actually calculate the formulate the problems. So these are the all things actually you need to know from chapter 7. Rest you can just ignore. So I will now directly go to chapter 10. So here I will not use the slides. I will just go through the whole chapter through the book. Okay, so I think it would be much more easier for you because I already have uploaded the book chapter. The first thing comes with the difference between the laminar and turbulent flow. This is very important. What is laminar and what is turbulent flow we already know. Just remember one thing about the laminar and turbulent flow, that the Reynolds, okay, so the scientist who actually used a dyed marker to check like what is the flow pattern, and he found like, if the velocity is very very low for a very viscous types of fluid, like the dyed pattern is kind of like very straight line, but if the velocity is higher or like the pipeline diameter is thicker, like the wider, and the fluid is thinner, that means lower viscosity, then the pattern, like the pattern is like this, more like this. Okay, so this is how the Reynolds number comes in. Okay, so Reynolds number Re equal to rho Vd divided by mu. So this is nothing but a ratio of inertia force over the viscous force. Okay, so the rho Vd represents the inertia force and mu represents the viscous force. So what does that mean? That means if the viscosity is higher, then what? Then the Reynolds number would be lower. That means the flow most likely would be laminar. If the diameter of the pipeline is lower, or a small diameter of the pipeline, then again the Reynolds number would be lower, so the flow would be laminar pattern. Again, the density and also the velocity of the fluid is low, that means it will have more laminar characteristics. It's like the same, the opposite pattern will observe for the turbulent. And what are the characteristics of the turbulent flow? Like if the pipeline diameter is, for instance, just imagine if a pipeline's diameter is very high, like 1 meter, 3 feet, or like nearly like 1 meter pipeline diameter, for instance, and the viscosity is not, it's like not high, it's like a lower viscosity, for instance natural gas. Okay, and rho of the natural gas and the velocity of the natural gas is also very high. That means what? That means the turbulence inside the pipeline will be very very high. Okay, so there will be a higher Reynolds number. But just imagine if the pipeline diameter is very small, like 2 millimeter pipeline diameter, and you are actually flowing a very viscous material, for instance honey, okay, and the velocity is very low, then what? Then you will get the velocity profile, like a short ended velocity profile, and that is totally a laminar profile. We have seen this difference back in our ANSYS simulation, right? So these are like the main differences between the laminar and turbulent flow. Now here the Reynolds number, you can actually write it in different forms, so it's just showing in here. So these are like the empirical relations, like the experimental results, and what it says, like if the Reynolds number is less than 2000, less or equal than 2000, then the flow is laminar. If the Reynolds number is more than 2000 but less or equal than 3000, well 3000, in some book you'll find 3000, some book you'll find 4000, or someone just play safe and put like 3500. So it is unpredictable. Okay, so this range we actually call it like a transitional range, or like transient range, or like unpredictable range. Okay, so it's kind of like work like laminar and turbulent, you can't just predict that range. Okay, but over 3000, or like over 4000 for sure, like the whole range is turbulent flow. Okay, now we know like how the laminar and turbulent flow profile actually looks like. Okay, so usually turbulent flows velocity profile, like the nose is really flat. Okay, but in case of laminar flow, the profile shows the nose is very steep. Okay, now again, in case of a laminar flow also, like after a flow actually flowing through inside the pipeline, after reaching to some length, the flow becomes this shape, like this fully developed shape. Okay, so we call this shape as a fully developed flow. That means the flow is now fully developed, and this length from starting till like developing the flow. Okay, so we call this length as LE, right? Or we can also call its length as the entrance length. Now there's a significance of this entrance length, because with this length we can actually now determine, like, okay, after this length this flow is fully developed. Remember when we actually worked on the ANSYS simulation, we always actually drew the velocity profile at the end, 8 meter. Okay, why? There was a significance. Why I actually choose the pipeline length 8 meter, because, and why at the exit, because if we actually choose in between inside the pipeline, then the velocity profile will be not fully developed. Okay, so 8 meter for that diameter. Okay, 8 meter was well for to have the fully developed. Now how we can determine that? Here is the formula. If the flow is laminar, then this is how, based on the diameter, this is how you can actually calculate the length. For instance, the flow is laminar, that means the value of R is 2000, and the pipeline diameter is 0.3 meter. That means it was for instance the pipeline diameter, yeah, 0.3 meter. So that means 2000 times 0.3 times 0.05, so you'll find the LE. But in case of turbulent flow, this is the relationship. Okay, so there is a relationship between the pipeline diameter and LE. So that means what? That means if the pipeline diameter is smaller, that means there is the flow would be less turbulent. Okay, so this is the pattern. So there is the math used in here, so it's a very simple one. I will not go through this math right now, but please do that, and if you have any question, just let me know through my email. Okay, now let's go to some applied for like the application of our knowledge so far we have learned. Okay, so when you actually design the pipelines, there are so many different units, there are so many different factors, and like Americans, they use different types of unit, and British and rest of the world actually use different types of units. So sometimes engineers actually or scientists, they will get confused, and what they do for that purpose, we have developed a universal convention of developing pipelines unit. What is that? We call these NPS, or nominal pipe size. Okay, so NPS or nominal pipe size has two different things. One is the NPS number one. Okay, here the NPS number. Another is we call it schedule number. Okay, so what is schedule number and what is NPS? NPS, just remember this. NPS actually it will give you the size, like the outer diameter. Okay, NPS relates with the outer diameter. Okay, this OD, NPS actually give you the outer diameter, like the idea about like the outer diameter. Okay, the schedule number is actually related with how much stress the pipeline can take, or mainly thickness. Okay, so if, just imagine, if the pipeline is more thick, then what? The pipeline can withstand with more stress. Okay, and if the pipeline is thinner, that means what? It can withstand with less stress. Okay, so that is actually the schedule number. That means if the schedule number is higher, that means the thickness is higher. If the schedule number is lower, it's the other way around. If the schedule number is lower value, that means it is the pipeline wall thickness, okay, would be small. But if the schedule number is higher, that means the pipeline would be more higher wall thickness. I think that yeah, this is the table. Here you will find. Give you an example. For instance, NPS 1, and this is the conversion chart. Okay, outer diameter for NPS 1 pipeline would be 1.31 inch, and always remember, when it comes with NPS and schedule number, always it will be with inch. Okay, after inch, then you can actually convert to other units, but always work with inches. Okay, so, or like yeah, we're actually working with the 1 NPS and 1.3 inch, the outer diameter, and it will mention like the schedule number is 80. That means the pipeline's wall thickness would be this one. So if we substitute like this minus this, we can get the internal diameter of the pipeline. Okay, it works as simple as that. Now here is the interesting thing. After the NPS number reached to 14, okay, the outer diameter and NPS would be same. That means if the outer diameter, if a pipeline is given like the NPS is 18, that means the outer diameter would be 18. You don't need any table to convert. You can directly go to that. Okay, so beyond 14, NPS and OD are same, right? And before, it is lower. I will actually add a chart, the conversion table. For that, I think I actually taught it in another course. I have that, not this one. I'll actually give you that one in this, the roughness. I will actually go through that later. NPS. Anyways, I'll actually give it to you later. Okay, so where is it? Okay, so this is how we actually convert the NPS and the schedule number. Okay, so to specify one pipeline, to know the internal diameter and the external diameter, like the outside diameter, we need two information. One, NPS, another is the schedule number. Whereas NPS gives us information about like the diameter of the pipeline, and schedule number gives us information on the wall thickness. So if in a math I mentioned NPS and the schedule number, so from this table you can easily get like the ID and OD, or internal diameter and the, or like sorry, inside diameter and the outside diameter. Okay, that's how it works. Now pipeline head loss. Okay, so this section will actually determine how we can calculate like the head loss. You remember like the last chapter, like the chapter 7, we already have learned what is head loss. Okay, so the Bernoulli's energy equation, we just add HL, which is the head loss. Now we'll actually calculate how we can develop the head loss. So in order to determine the head loss, the engineer Dorsey and Weisbach, they actually developed a formulation. You don't need to go through the whole detail of it. Okay, we'll just go to the final form, and that is HF equals to a factor times L by D V square by 2G. Okay, and this factor, this is the head loss, HF. Okay, HF is the head loss, that the same head loss we have used in here. Is, you see, the Bernoulli's equation, P by gamma plus Z equal to P2 gamma by Z2 plus HL. Okay, so this HL is equal to this one. I mean, don't confuse with L and F, it's the same thing. They just, I mean, use the new symbol HF. It's just the head loss. Okay, so this head loss equals to L by D V square by 2G times a factor, and this factor is known as friction factor. Okay, so this is a very important formulation. Just remember, I mean, you don't need to remember what is friction factor means, because usually we determine friction factor in another way, not putting all the values in here. Okay, I will show you how we actually determine the friction factor. But what is friction factor? Friction factor is shear stress acting at the wall times the kinetic pressure. That means it's a stress acting at the wall. Okay, now friction factor have different types of friction factor. Now this is we call Dorsey friction factor, because this is definitely the Dorsey-Weisbach equation, so that's why we'll actually call this thing a Dorsey friction factor. But if you actually divide Dorsey friction factor times 4, we call this fanning friction factor. Okay, just remember that. You don't I mean, this is just the information, just a FYI. But the most important thing is this final form. Okay, so H, or head loss, equal to friction factor times L by D of V square by 2G. Okay, so this is the Dorsey-Weisbach equation, the most important equation in this chapter. There is another equation is important, I will show you later on. Stress distribution of the pipeline, you don't need to go through this thing, we'll just skip this part. Laminar flow of a round tube. Now you remember like the velocity profile of the laminar flow, how it looks like. We drew the velocity profile and through the Excel, and later we've seen how it looks like. This exactly looks like this equation. Okay, and this is an equation for a parabola. Okay, so that means the velocity profile here, it proves that the velocity profile exactly looks like the parabola. Okay, so V equal to V max of 1 minus R by R naught square. What is R? This is the R naught, like the diameter of the pipeline, and R is the specific points, each different points. So if you know V max, if you know R naught, so for different R you can get the different V. The exact same thing we did with our ANSYS Fluent that project. Okay, that project 1. But we'll see. So this is the velocity profile, like the parabolic shape. It just showed that one. Okay, and we also know another information, that is this Vmax is what? This Vmax is half of the average velocity. Okay, so this is how we actually get it. So the mean velocity, or the average velocity, is equal to half of the maximum velocity. Okay, so like here somewhere, like that. Okay, head loss again. So HL, if so this is, if this is the point 1, this is the point 2. So at the Bernoulli's equation, what do we know? P1 by gamma plus Z1 equal to P2 by gamma plus Z2 plus head loss due to the motion. That's why these velocity terminologies are not in here. We just replace it with head loss. And as we know, HL and HF, these are same. Okay, so just don't confuse it, they're same. So HF equal to this one, f of L by d v square by 2g. For laminar equation, using the Darcy-Weisbach for the laminar fully developed flow, F equal to 64 by R. Remember this equation, very very important equation. If the velocity is given as laminar equation, you don't need to use any chart or anything to calculate friction factor. You can just use this one. If the Reynolds number is given, then just divide Reynolds number with 64 and you will get the friction factor, and you can plug the friction factor into this formula and you can get the HF, and from HF, if you plug it in here, you can calculate, like if P1, Z1, P2, Z2, whatever is given to the, you want to calculate, you can just draw that. Okay, so this is one of the example how to do that. Go to this example again, solve it, and if you have any question, just let me know. Now for laminar equation, it's really easy to calculate, as we can see. Okay, what about the turbulent? For the turbulent, it's not that easy. Okay, for the turbulent, we have lots of different types of things, like look at here. So what's happened, like the scientists, and they actually try to determine how to work with the turbulent flow. And Darcy is one of the student. Darcy's student, his name is this one, Nycreds. Okay, so he actually worked with an experiment, and that experiment results actually to develop a friction factor. Okay, so what's happened from his result, he actually developed a nice chart for the wall roughness. Okay, and then the scientist Moody, he actually developed a diagram based on his experiment, and also a formula. That's a formula's name is Colebrook-White formula. Okay, based on them, Moody actually developed a diagram, and this diagram known as the Moody's diagram. Okay, now let's actually explain you the Moody's diagram a little bit. I will just switch to the slide, because the Moody's diagram is given better in here to interpret. Okay, this is the Moody's diagram. So this is we called semi-log diagram. Okay, what is semi-log diagram? Because here it's the normal, like 0.008 to 0.1, the friction factor, that the y-axis, but the x-axis, it is a it's the log chart. Okay, so that means here is 1, this is 1000, this is what, 2000, 4000, 6000, 8000, 10,000. Okay, so this is how it works, because the Reynolds number is always very high. And here, the parallel axis with the y-axis, we have the relative roughness. Okay, and here is the like the this if we use this equation based on that, but you don't have to worry on this too much. So how we can actually calculate that is, as we already know, less than 2000, okay, or like 2500 nearly like that, we can use the laminar flow, and that is F equal to 64 by R. So if your Reynolds number is given and it's all said like it is laminar flow, then what? For instance, your Reynolds number is 1000, so how you can actually draw that? So you can draw that like this. Insert I'm just trying to find one draw. Okay, so 1000, this is the laminar flow, okay, and so the friction factor would be 0.06. okay, this is how we calculate the friction factor. Now if it's said like if it is a turbulent flow, then what we will do? For instance, your Reynolds number is given, okay, so if your Reynolds number is given and this is like 10 to the power 6 into 10 to the power 5 like here, okay. All right, so let's try to calculate now. 6 to 10 to the power 5, here we got it, and it's saying it's turbulent flow. Now we have to calculate the friction factor. Now when you actually go up, you can find like there are lots of different 3 or 4 like 30 or 40 like these lines, okay. So these lines are known as the relative roughness lines, okay. So not only the Reynolds number is important, you have to know the relative roughness of the pipeline to calculate the friction factor. So that means depending on the diameter of the pipeline and the pipeline properties, that means it's made up with glass, with steel, with new steel or old steel, with like the corroded pipeline, okay. For instance, if the pipeline is corroded, then what? It totally makes sense. Like we know, like if the pipeline is corroded, that means it got more friction, and if the pipeline is new, there will be less friction, okay. So for corroded pipeline, for the new pipeline, there will be so many different types of combinations in here. So based on that, we'll actually select one line and then we'll calculate the friction factor. So these are actually explained in here, okay. So this is the K value, okay, in millimeter or in inches, okay. So depending on like which unit actually the chart is given here. The chart is given in it will be written in like, okay, so which unit it is given, and you can actually calculate that, okay, depending on like the diameter of the pipeline, how we can actually determine. Like if you select millimeter, your diameter of the pipeline should be also in millimeter, and that's how K by D will be a dimensionless number, okay, like this. If your diameter is in feet, convert it to inches and select the K value in inches and then make the K by D, okay. So the value of K for glass and plastic you see in almost 0, that means it's smooth. But for more irons or something with more frictions, it will be way more. Like for instance, the copper is almost smooth, but in case of like asphalted cast iron, it's higher, okay. And concrete is way higher, because we know concrete surface is not smooth at all, right? So this is the relative roughness chart, and from there it will be given at your problem, okay. So from there you can calculate the K by D, and from there you can actually, if you know the Reynolds number, you can easily calculate the friction factor, okay. Alright, so yeah, that's how we solve the problems. Let's go through one problem and let's solve it. Like here it says water flows at a rate of, we have the flow rate 20 centimeter asphalted cast iron pipeline. That means from that chart we can actually get what the K value, what is the head loss per kilometer of the pipeline. Okay, so length is given 1000 meter or 1 kilometer. D is given, okay, diameter is 0.2 meter, that means that 20 centimeter or 0.2 meter. Asphalted cast iron, here the millimeter is 0.12 millimeter. Okay, it's the K. That means we can actually calculate the relative roughness 0.0006. okay, now we have to calculate the Reynolds number also to get the friction factor. So Reynolds number is, we know, rho v by nu, or you can reduce to this equation and we can actually calculate the Reynolds number. We know relative, this is the roughness and this is the relative roughness, and from there the relative roughness is 0.0006 and Reynolds number is 3.18 times 10 to the power 5. So 3.18 times 10 to the power 5, sorry, 3.18 times 10 to the power 5, that means like nearly 3 here, and 0.00006 this one. So friction factor is nearly 0.2. okay, here you see, sorry, 0.02, okay, or 0.019, and then you can just plug it in this formula and you can actually get the head loss. Okay, so this head loss is the equivalent loss. Okay, what it says, it says like if the same diameter's pipeline, if the flow pipeline length is like 1012 meter, like 12, if you extend the pipeline 12 meter more, then the pipeline's law would have the loss, it's the equivalent, the same loss to here. Okay, that's what the head loss. So head loss, we express it through the length of the pipeline. Okay, now it's clear, hopefully, and if you have any question again, just let me know. Okay, you can solve this problem and you can do it later. All are the similar problems. Okay, just go through this problem and I will highly urge you to solve it. Okay, now minor loss coefficient, or K. So head loss of a pipeline is for the straight pipeline. What's about if your pipeline got some joints, parts, components like elbow, valves? Okay, so for those you might have some minor losses. So head loss is known as major loss, and the pipeline components, the loss, the pressure loss due to the pipeline component, are known as the minor loss. Okay, so how we can calculate the minor loss? The minor loss equal to K of V square by 2G, where is K is the minor loss factor. Okay, so each different type of pipelines entrance, expansion, or like different types of parts and components have a minor loss is given. Okay, so this K value is given, and if you know the K value, like for instance a globe valve wide open, the K value is 10. Okay, that means the value is very very high. Okay, but for a 45-degree elbow, K value is only 0.4. okay, so if you know the K value, you can just put it in this formula. Okay, and you can actually calculate the head loss or minor head loss. Okay, so the total head loss, what will be the total head loss? The combined or the total head loss would be head loss due to the major head loss of the pipes and head loss due to the component. This is a very very important formula. Just folks, just remember this. Total head loss equal to the head loss due to the pipes or the major head loss, which is summation. That means if the pipes are branches, like you have 3 or 4 different pipelines, it would be summation of all pipeline of the friction due to the uh, fluid flow inside the pipeline, or we can get this F from Moody's diagram. Okay, L by D V square by 2J plus, for the components, what are the components we have, and the K value for the components, what are the different types of components, the K value we have seen at the chart before, and V square by 2G. Okay, so that's how you can actually calculate the whole total loss, total head loss. Okay, all right, so let's see a problem, and that will actually give you better understanding. So 10.7, if oil, the properties are given, flows from the upper to the this lower reservoir, and you can see there are some pipeline branches. Okay, so it's given it's a smooth pipe. If the smooth pipe is already told, that means what? That means there is no pipeline head loss. Okay, but it got some minor losses. Okay, so there is no major loss, but there are minor losses. What? We have bends, two bends, right? So there are two different bends, and it is given, and there is entrance loss and exit loss. These are also formulated, and then we can actually calculate the total loss combined and get the equation. So I'm pretty much sure you can actually go through the problem, and you can actually easily solve the problem. And if you have any questions, just let me know. Now, if the pipeline is not circular, if it's a conduit, then the formulas would be the same, but instead of the diameter, we actually use an equivalent diameter. That's we usually called hydraulic diameter. Okay, so the formula of hydraulic diameter is 4 times cross-sectional area divided by weighted perimeter, and weighted perimeters means like how much area the fluid is inside of the pipeline. Okay, so we have a formula for that. So formula is twice LW divided by L plus W. Okay, and W and L is the and then the width, so we can calculate the hydraulic diameter. Okay, so just remember, for a circular pipeline, D and DH are same, but if the pipeline is not circular, then only at that time we need to calculate like the hydraulic diameter. And as you know, if the pipeline is not circular, the width and the breadth would be already given, so you can just calculate the hydraulic diameter from this formula. Okay, so this is one of the example of that. Pump, again, we already know what is pump. Pump is a device from, we actually, the input is energy, we put energy in the pump, and the impeller rotates, and we got the fluid flow. Okay, so this is the equation for the pump. You just need to remember the pump equations in here. Okay, this HP is the, from here, the head of the pump head, we can actually develop the curve from there, and this is the problem based on that. Okay, based on the pump head. Please go through the problem, and again, if you have any question, just let me know. The pipeline networks, so different pipelines, different networks. If you can, I'll just skip this part now. Okay, so that's it. That's your total syllabus of your final exam. And again, the final would be a take-home exam style. And remember, if anyone failed to appear or submit the final take-home exam, then the result will not be published. Okay, so keep remember that. Okay, so good luck, best wishes, and stay home and stay safe. Goodbye, everyone.